All right, so let's see. So Friday we'll have the exam, and it'll be exactly the same as we did exam 1. Send it to you. You'll turn it in by the end of the day on Friday. Does that sound good? And that worked pretty well with everybody? Yeah, I'll send it. I'll probably do the same thing. Didn't I send it the evening before?
Yeah.
So that way you could at least have the time during the day, right? And then what did I make the due date, the time? I don't remember. Well, whatever. It's not really going to make that much of a difference if you already have a certain, if you have enough time anyway. So Wednesday maybe we'll do some kind of review. I think I posted on Blackboard the topics, which goes pretty much from trees up until the polyhedral stuff. I would just use the homeworks and the extra problems that I made, right? Normally when I teach this, I suggest you guys memorize the definitions really well, but since that's probably not going to be a component of the exam like it normally is, I mean, you should know the definitions really well, because if you don't, it would make it much more time consuming to try and attempt some of these problems. But I mean, you guys probably know that that's key to studying for this course. So what we're going to do today, I'm sorry? Yeah, especially anything beyond like discrete. I mean, even in discrete, you really have to know the definitions really well. In calculus, you can kind of get by because you can just memorize methods and stuff. But when you're proving stuff, you need templates and definitions really well, so to know those. Okay, so today we'll talk about coloring, but this won't be on the exam. Okay, so this will be on the final. All right. And all right. Okay, so what is a coloring? So what we're going to talk about right now is vertex coloring. Okay, so a vertex coloring of a graph. Normally, if you just say coloring, it means a vertex coloring. You can color edges, but you would say an edge coloring. But usually if you're reading something and someone's talking about coloring, they're usually talking about a vertex coloring. So vertex coloring of a graph is an assignment of colors to the vertex set in the graph. Okay, so formally you could just think of it as a function from the vertex set to the set S, where S is a color set, and you can make S whatever you want. You could color your graph with elephants and purple if you want. You could use actual colors, but to make things as simple as possible, usually you just use the numbers 1 up to k, where k is just some positive integer, okay? And if your coloring set is that set right there, then we call F a k coloring, because you're using essentially k colors there. And it's a lot faster to use numbers than to actually take out your pens and try to draw all the colors. But you can, of course, think of each of them as some kind of individual color. Okay, so from now on, we'll just say coloring when we're talking about vertex coloring. And then any other type, we'll make sure to add the designation there. Okay, so that's a coloring, pretty general. Actually, let me just show you an example of a coloring, right? So let's say that I had 3 cycle or K3, right? So let's just color all the vertices with the number 1. So this is a 1 coloring. Okay. Technically, you could think of that thing also as a 2 coloring, a 3 coloring, or a 2000 coloring. I just happen to only be using the numbers 1 for it, right? Can also call this a 2, 3, 4, coloring. You just happen to only be using the number 1 there, okay? So in general, a coloring by itself is your, one question that could be interesting is, what are the total number of colorings I could give a graph? That by itself is not difficult of a problem. So think about that just for a second. You probably can solve that. But if I add this additional condition that I have a proper coloring, which satisfies this condition here. So a proper coloring is a coloring where adjacent vertices have to have different colors. Okay, so that is a proper coloring. You can think of it again as a function, but then it has to satisfy this universal condition. So for all u and v in the vertex set, if they're adjacent to each other, then the the colorings have to be, the colors have to be different. Okay, so this is not a proper coloring, right? So this right here is not a proper coloring because certainly I have adjacent vertices that are not colored differently, right? These two are adjacent and they're colored the same. So immediately if you identify a pair, such a pair, then you know that it's not a proper coloring. In fact, if you just look at the negation of this, there would exist a pair, right, where they're adjacent and this is, they're actually equal, right? So how would I make this proper? Well, if you think about it, in a complete graph, every pair is adjacent to each other. So in a complete graph, you would actually have to make sure that all the vertices are colored differently. So in fact, I would need 3 colors to properly color this, right? For example, let me just walk you through the procedure. If I color this 1, now this adjacent vertex has to be colored different. So I'll color this 2. And now this vertex is adjacent to both of these. So I have to use a new color. So I'll use 3. Okay. So you can call this a 3 coloring. But more specifically, and it is proper. So it would probably it's better to just call this a proper 3 coloring. Okay, and technically you could say that it's also a proper 4, 5, blah, blah, blah coloring. Okay, also a proper 4, 5, and so on coloring. I just happen to not be using those additional available colors. Okay. Now, one interesting problem is if I give you a graph, what is the minimum number of colors I need in order to properly color the graph? And therefore, even though that I have, as soon as I figure out that it's like a proper 6 coloring, of course it's a proper 7, 8, 9, and so on coloring. But you want to figure out what are the fewest number of colors that I need to properly color the graph. Okay. Now, does everyone agree that this is a little bit more interesting than just finding colorings of the graph? Because if you think about the coloring question, you're not even looking at the structure of the graph. You're just essentially labeling the vertex set with numbers, right? So if you were to count colorings, it's very simple, right? You would have, if you're using k colors, you would have k choices for each vertex. They'd be independent. So it would be k to the n, where n is the number of vertices, right? But a proper k coloring, surprisingly, finding these in general is quite difficult, actually. Okay, and there's a ton of research done on this. Okay. Okay. What's another type of structure that we encountered in this class? Well, path graphs, right? So this graph, if I color this first vertex a 1, I certainly have to use a different color for the second vertex, 2. And now I can actually reuse 1 because it's not, this vertex is not adjacent to the next one. So I can actually reuse 1 again, right? So these are different. Now I can reuse 2, and now I can use 1 again. So look, this is actually it's a path graph, and it's a proper 2 coloring. In fact, these path graphs are part of a much larger family, which I hinted at the beginning of the class, which is bipartite graphs, right? I mean, you guys know bipartite graphs really well, but one way you can think about a bipartite graph is the fact that it will always have a proper 2 coloring. So for example, if you look at let's just make up a complete bipartite graph, maybe K2, 3. Okay, so 2 vertices on the left, 3 on the right, and complete, they draw on all the possible edges. So this vertex will be connected to all 3 of these. This vertex will be connected to all 3 of these. Okay. And now, if you think about it, all the vertices on the left are not going to be adjacent to each other because they're in the same partition set, right? So I can color those the same. Let me stick to red here. So I can color all these the same, and I can color all of these the same, because within a partition, they're not going to have any adjacencies, right? And all the adjacencies are going to go from one partition set to the next partition set. So all you really need to do is just make sure that the 2 partitions are colored differently from each other, right? So this is also a proper 2 coloring. And so from this, you could probably guess a general theory, what I'm trying to do here is throughout this course, I hope one thing that you guys have noticed is just trying examples doesn't prove anything, but it definitely reveals certain properties that you could then attempt to prove. So for example, this reveals, well, path graphs, maybe they're always proper, you can always properly two color those. And then more generally, bipartite graphs, right? Aren't path graphs bipartite graphs? Why is that? Yeah, okay, so you go back to the original definition, but we have another theorem that we can utilize here, right? Do you remember what theorem classified bipartite graphs? Yeah, the Koenig's theorem, right? So there's no odd cycles, so that means it's bipartite. So bipartite, it's fairly simple to prove that they're properly two colorable because of, well, the discussion that we just said, right? I mean, you can write it out systematically, but within a partition, no adjacencies are going to be there. So you can color all the vertices within a partition the same. But then between partitions, there may be edges. So therefore, you would want to color those differently. Now, if there were no edges, then you could just simplify it and you would, I mean, what would you have there? If you had no edges, then you would pretty much have isolated vertices to begin with. So you don't actually need two colors there. You wouldn't need two separating partitions. So you'd have to think about the trivial cases, right? What's the smallest one and so forth. But you can give me the general theory and then look at the extreme cases. Okay, but this is helping us see where we're headed with this. Okay, so next, going off of that bipartite condition. So suppose F is a K coloring, okay, just in general, and suppose V sub I is a set of vertices that are colored I, okay, where I is going to be between 1 and K inclusive. In other words, what you're really saying is VI is the collection of vertices such that F of V is equal to I. Okay? So as long as this vertex set is non-empty, so there actually is a vertex in the set VI, then we call VI a color class. Right? And furthermore, the non-empty elements of the set of these color classes forms a partition of the vertex set. So this is kind of interesting because it's a method of partitioning the graph up, at least by vertices. Right? So let me give you an example of this. Okay? So let's look at this graph. Okay. So here's my graph. And what I'm going to do is I'm going to color the vertices. Okay. Okay. So up here, notice within this graph, I have a subgraph that's a K3. So I certainly actually am going to need 3 colors there, right? So 1, 2, 3. Okay. But now 3, this vertex over here is not adjacent to the ones that are colored 1 and 2. So I could reuse any of those 2 previous ones. So maybe let's choose the smallest one that's available, which is the 1. And now I can proceed around this cycle, 2, 1, 2. But do you see I get to this sort of condition here that I can't color this last vertex a 1 or a 2. So I have to color this a 3, something different. Okay. Now the procedure that I just showed you there, you can't always just traverse the graph in a nice way and assume that you did it in such a way that you're minimizing the number of colors. So doing that is actually quite complicated in general. But I can guarantee that this graph actually needed 3 colors anyway, because the fact that this K3 is in here. Okay. You can actually also say that it has to have 3 because there's an odd cycle in here, but we'll get to that a little later. Right? So you kind of look for within a graph these substructures that force a lower bound on the coloring set, the number of colors you need, and from there it can help you. And I'll kind of explain that as we go. All right, so does everyone at least agree that I definitely needed 3 colors to properly color that graph, and I have produced a proper 3 coloring? Okay, so now what do I mean by this coloring set here? Well, I didn't actually label the vertices. So in this problem, because I'm actually going to partition up the vertex set, let's also label the vertices. Doesn't really matter which ones that we call. So V1, V2, V3, V4, V5, V6, V7, V8. Okay. Okay. So now the color class is just write out which things are colored. So which vertices are colored 1, which vertices are colored 2, and which vertices are colored 3. Okay. So vertices that are colored 1, V1 is colored 1, V4 is colored 1, and V6, and no others, right? So those are the only 3 that are colored 1. The ones that are colored 2, we have V2, V5, and V7. And then vertices that are colored 3, V3, and V8. Now, do you guys agree that these 3 sets, this set here, the set V1, V2, and V3 is a partition of the vertex set? Did we talk about partitions in this class? So do you guys remember the definition of a partition? A partition of a set is just you're looking at subsets of the set. Okay. Do you agree that these are all subsets of the vertex set? You remember the other 2 conditions that a partition has to satisfy? Yeah, they got to be disjoint so they don't share any vertices. Okay. You kind of think of them as taking a cake and you're slicing it up into pieces, right? But then the last condition is they got to be non-empty. So you can't have like a non-empty piece. Okay. So is everything non-empty? Actually, there's one more condition, which is probably even more important. Yeah, the union of all of them is the whole vertex set. Okay. So non-empty, disjoint, the union is the whole. Okay. So do we agree that this is a partitioning of the vertex set? Okay, cool. Anyone remember why partitions are so useful? Because practically everything in math is partitions, right? Everything in math is you have some object and you're looking at the equivalence relations of that object, and then you're studying the equivalence classes. And anytime you have a partition, that actually gives rise to an equivalence relation on the set. So in other words, you could say 2 vertices are equivalent if they're colored the same, in a sense. And this would be the partition induced by that relation. Yes? Sorry? Yeah. So you can think of these as equivalence classes. Yeah. Under that relation. Like 2 vertices are colored, 2 vertices are related if they're colored the same. And to be an equivalence relation, do you remember the 3 things that have to be satisfied? You have to be reflexive. So is every vertex colored the same as itself? Yes. Is if a vertex A is colored the same as vertex B, is vertex B colored the same as vertex A? Yes, that's a symmetric property. And then transitive is the same, right? If A and B are colored the same and B and C are colored the same, then A and C are colored the same, right? Okay. What's interesting is no matter what, if you have a partition, that gives you an equivalence relation. And if you have an equivalence relation, that'll always give you a partition. So there is a correspondence between those things. And that's everything in math. Like you usually have some object and you are studying the equivalence relations on that object. Like how are these things equal? You're generalizing the idea of being equal, right? And it's beyond just math too, right? Like usually when you're classifying things in other subject areas, you're doing kind of that, but they don't do it as formally as we do it, right? Okay, now the minimum positive k for which G is k colorable, we actually call that the chromatic number of the graph. And we use chi there. So Greek letter chi. Okay, so a graph where chi is equal to k, we actually call that a k chromatic graph, right? That should probably have been bolded right there. But okay. Therefore, if chi is equal of the graph is equal to k, then there must exist a k coloring of G, but not a k minus 1 coloring. Hang on, can I just look back here? Should really say proper, I think, right? The point is that it contains a proper K coloring. Oh, but I said the word, you see, I said the word K colorable. So K colorable means that it's a proper coloring, right? Is that what we said on the front? Yeah. So a graph is K colorable if there exists a proper K coloring, right? So you can, so those are interchangeable. K colorable, proper K coloring. But if you just say K coloring, then you're dropping the whole proper condition, okay? So just back here, because of the way that I wrote it, so there should exist a proper K coloring, or you could say it's K colorable, but not K minus 1 colorable. So you can fix that either way that you want, but this should definitely be a proper, but not a proper. Okay, does everyone agree with that? So you can either insert the word proper right here. So there would exist a proper K coloring, but not a proper K minus 1 coloring, right? So you need K, at least K colors. Okay. Or the other way you could fix that is you could say that it's K colorable, but not K minus 1 colorable. I don't know. I didn't come up with these definitions. I think it's actually probably better to just always use the word proper when you're talking about coloring, so you don't screw that up, because I myself obviously screwed that up, right? So that's just my own suggestion. I probably would just stick with keeping the word proper there. Okay, so there is no general formula for the chromatic number of a graph. In fact, the problem of showing that a graph is K colorable belongs to the class of NP complete problems. So in other words, it's very difficult to not only, I mean, it's very difficult to actually find it and verify it. So if I claim that it's a proper K coloring and that is the chromatic number, it's not quick to just verify it, right? Like, let me give you an example. So did I talk about NP kind of before? Okay, so the example I like is if I give you a huge integer, right? And I ask you to factor it. In general, that would take you a long time, right? But if I give you the prime factors, it's very easy for you to check if that's the prime factorization, because all you got to do is just multiply the numbers together and see that I didn't lie to you, right? Another example would be if I gave you a polynomial and I said factor it into its roots. If I gave you the solution to that, the roots, it's very easy for you to check that those are the roots of the polynomial, right? So it's not easy to solve in general, but quick to check, right? This is a type of problem that it is not only hard to solve, but it's actually hard to check it, because I could make an outrageous claim, but then you got to go and then verify it. That's not an easy verifiable thing, okay? Coloring, this is kind of funny, right? In this class, counting is hard, coloring is hard. It's like I'm destroying your childhood, right? So yeah, so there's lots of methods for doing this, and I'm going to kind of slowly go through some general techniques that you would use. But this area of research is still very wide open. Usually what people do is they try to classify what the chromatic number is for particular types of families of graphs. So the simple ones we can do right now, like the complete graphs, bipartite graphs, and things like that. But in general, there are lots of families, and if there's no general formula, you try to come up with maybe a formula for some describable family. Okay, and believe it or not, this has a ton of applications for all sorts of random fields. Okay, because you can kind of think of the colorings as they can be applied to it. Depends. I mean, there's endless applications for it. It's just you're trying to come up with configurations where things are they share common characteristics, but also have to be different from each other. Okay. Okay, let's go through some general observations. So first of all, let's start with some fairly simple ones. So first one, the chromatic number has to be less than or equal to n, where n is the number of vertices, right? N is the number of vertices in the graph. Okay, why is that? Well, there's only n vertices. So if I chose to color all the vertices differently, that will certainly always produce a proper coloring, no matter how many edges I have in the graph, right? So clearly, if G has n vertices, it is n colorable. In other words, I'm just probably going to always say that it has a proper n coloring. Does everyone agree with that? You could kind of think of the extreme case, which is the complete graph, okay? So that's observation 2. The chromatic number for the complete graph is actually always going to be n, right? And you should be able to prove that pretty short, I mean, with not very much, okay? So I'm asking you why you should be able to prove that. But if you look at the original definition of a proper coloring, it's saying if two vertices are adjacent, they have to be colored differently, right? And you have the definition of the complete graph where every pair of vertices is adjacent, because this is going to force this extreme condition, right? Okay, so for example, this is K5, right? This vertex is adjacent to all of these. So I have to color this with a 2, okay? But now 2 is not only adjacent to 1, but it's adjacent to this one over here. And if I try to use 1 again, it's adjacent to this one. In other words, I have a K3 within this, right? And you also have a K4 within this, so I'm going to need a 4th color. And then finally, every pair of vertices is adjacent. Okay, so it's going to force this condition. If you were, okay, here's another way to think about it. If you were able to color two vertices in the complete graph the same, that would mean that they are not adjacent to each other, right? But in the complete graph, every pair is adjacent, so therefore that's impossible. So I guess I just proved it by contradiction for you, right? But you don't even need to do that. I think you can just think of it directly, right? But proof by contradiction is the best, so. Everyone okay with that? So it's always good to try to come up with bounds, okay, and then think about which types of graphs achieve these bounds, you know, these extreme cases. Okay, next type of graph, let's look at path graphs and cycles and so on. Okay. So the chromatic number for Pn for a path graph is equal to 2 as long as n is greater than or equal to 2, right? I mean, if it's just a single vertex, then you don't need two colors, right? Everyone okay with this? Now, the way I would probably just prove that in general, I mean, you can of course use the definition. If we later look at the bipartite graph situation, this is in that family, a bipartite graph. So I would just use the bipartite proof to get us to that one, okay? And then cycles are kind of interesting because sometimes cycles are bipartite and sometimes they're not, right? When are they not? When they have an odd cycle, right? Yeah. So when they're odd, yeah, same thing. I mean, they're only one cycle to begin with, right? So if they're odd, they're not bipartite. So we might actually need more than 2, right? And that's pretty much actually what exactly happens. So it's 2 if n is even, right? You can either write n mod 2 is congruent to 0, or you could just say n is even. And then it'll be 3 if n mod 2 is congruent to 1. N is odd. Okay. The being 2, that will also come from the bipartite situation. Being 3, well, if it's odd, it's not going to be bipartite, but then you could show me why you would need the third color there. Okay. In fact, we can actually add a proposition here. Proposition. Proposition. If the graph in general, if G has an odd cycle, then the chromatic number for G has to be at least 3. So you definitely will need at least 3 colors to properly color the graph. Can you think of the proof of this? If it has an odd cycle, it's not bipartite, which means that you can't properly color it with 2 colors. That's pretty much it. Okay, so the proof, if G has an odd cycle, it's not bipartite by Koenig, which means that you would need at least 3 colors to properly color this thing. Now, getting this lower bound does not mean that you actually know what the proper coloring is. So for the case here of it being an odd cycle by itself, to get that it's actually 3, you would just have to explain why you will be able to achieve a proper 3 coloring, okay? Kind of, the way you can kind of think about it is it'll follow the even pattern up until that pretty much last vertex, and that's the only one that you'll need to color with the 3rd color, actually, if you look back at the definition of this thing, right? Let me give you an example. Well, I should probably give you an example of both of these. Okay, so example up here. Okay, so here's C4. I only need 2 colors as I go around, right? So I reach this last terminal sort of vertex, and it's different. It's not going to cause some kind of contradiction to the coloring. It's not going to contradict the properness of the coloring. But if I have an odd cycle, say with C5, right, I can follow this around 1, 2, 1, 2, but now I get to the point where I cannot color this 1, which was the initial vertex coloring. So that's where I have to use this 3rd coloring here, right? Now, another way to think about this, again, is by proof by contradiction. It's really funny that all these things are structural, right? If you were able to color that with only 2 colors, then that would mean it's bipartite, right? Because you should be able to color one partition set with 1 color, one partition set with another color, and therefore you would be saying an odd cycle is bipartite, which would contradict Koenig's theorem. Okay, but I think, again, you could just use the actual definition of both the cycle and the proper coloring, but I prefer proof by contradiction if it makes the proof 2 lines versus 5 lines, right? And so on. So everyone kind of see that that's what's kind of happening. Like if it's even, certainly I can create a partitioning, right? I can put all the 1 colors in 1 partition set and so. Let me give you an example of something like this. So a graph that has an odd cycle. Well, actually, that one that I showed you before is an example of that. You see that it has an odd cycle. I needed 3 colors. Same thing here. Even if I didn't have that part, it has an odd cycle, and it required 3 colorings, 3 colors. But let's just do another one. So this graph, so G has an odd cycle. So what does that tell us? Well, that tells us that the chromatic number is at least 3. Okay. So this is a general procedure. If I told you to prove what the chromatic number of a graph is, it's very useful to tell me why it would have to have a lower bound. Okay. So usually you look at a subgraph and say, okay, either you can argue, okay, it has a K3 in here, and you could say the same thing actually, that it's at least 3. But just going off of this proposition, it has an odd cycle, so it's at least 3. Everyone okay with that? Now to prove that the chromatic number is 3, now that I know that it's at least 3, all I have to do is actually produce for you a proper 3 coloring, and that would show you that the chromatic number is less than or equal to 3, and therefore it would be equal to 3 by these 2 bounds, right? So let's try to find a proper 3 coloring in G or of G. So can we do that? So 1, 2, 1, 2, and now 3. right? I need a 3 here. And then going back over here, can I do 1 and 2 here? Is this proper? Everything is adjacent, is different colors. Good. So do you agree that I have found a proper 3 coloring? So if you wanted to be very technical here, producing the coloring shows you an upper bound. You see that? So the above shows the chromatic number is less than or equal to 3, right? So if you produce a proper K coloring, then that'll give you an upper bound. And then you kind of use the subgraph structure plus the proper coloring you produced, and that'll narrow the window of the possibilities. So thus, the chromatic number is now actually got to be 3 exactly. Okay, that's the most powerful technique, really, to be honest. Find a clever lower bound, produce a proper coloring, and see if you can narrow the window down as an upper bound. So far, the only upper bound that I gave you is n, which is terrible, right? So the lower bounds are nice because you can use the classifications to see if those are within the graph in some way and expand on it. Okay, which brings me to observation 5. So if H is a subgraph of G, then the chromatic number of H is going to be less than or equal to the chromatic number of G. The proof of that is really short because it's going to inherit any adjacencies that you choose within the graph, right? So, but it might not have all of them. So certainly if you have a proper coloring for H, it's not going to be a proper coloring in G, but you can prove that it's less than or equal to G because of the fact that you're not going to use all of the adjacencies from the bigger graph. Maybe see if you can prove this. I'm trying to think of the shortest way you could possibly prove that. Okay, now let's see if we can go back to our bipartite condition and actually prove it, which would then prove some of the previous things if you use this result or classifying it in general. Okay, so chromatic number for a graph is 2 if and only if G is bipartite. Okay, so let's go this way first. So suppose G is bipartite. With partition sets, U1 and U2. I guess we could just call them V1 and V2, which is perfect because of our previous notation. Okay. Right. So I have vertices in each partition. There may be some edges, right? But all the edges have to go from one partition set to the other partition set. So all I have to do is color this partition. Color all the vertices in partitions at V1 with 1. I can do that. Why is that? Well, within a partition set, you're not going to have any adjacencies. No vertices in V1 are adjacent. So this is proper. Does everyone agree with that? So no vertices in V1 are adjacent. So far that coloring is a proper coloring. And similarly over here, I can color all these vertices. 2. No vertices in V2 are going to be adjacent to each other. So this is maintaining the fact that it's a proper coloring. And the reason that I can't use 1 again is because there may be vertices from partition set V1 and V2 that are connected to each other. Okay. Now, to be a bipartite graph, you at least have to have a single. Usually, you require there's at least an edge in there. I guess you could I'm trying to remember in the original definition. can you allow partition set to be empty? It seems like it would be kind of a boring bipartite graph to do that. But if you do this, right? Therefore, the chromatic number would be 2, right? If you want to be super picky about this, you could say that this shows that the proper coloring is less than or equal to 2, right? Because you produced a coloring, right? And then now you got to verify, why is it at least 1? Well, as long as there's an actual edge in the graph, then you have to color the 2 vertices different, right? And we know that the edge, any edge that exists would have to be from one vertex in V1 to one vertex in V2. Okay, so if you want to add that tiny little bit in there, then that would be it. So if you go back to the original definition of bipartite and you allow one of the partition sets, if you allow no edges, then you would have to add that as an extreme extra possibility, which would be a really boring one, really. Okay, because you just have isolated vertices. So as long as you have a bipartite graph where you at least have one edge in it, which I would imagine actually should be required in the definition. But even if it isn't, as long as it has one edge, you definitely will need 2 colors, and that'll be maintained through the whole. Is everyone okay with this? Okay, what about going the other way? Well, if the chromatic number is 2, then you could do this exact same thing, because you can do the color class thing, right? You'd have 2 color classes, and therefore you're partitioning the graph into 2 partitions, and it's proper, so therefore it'll be bipartite. Okay, so going the other way, okay, if the chromatic number is equal to 2, then the color classes V1 and V2 partition V into a bipartition. Good. All right, so now that we have this general result for bipartite graphs, that would tell us the chromatic number for complete bipartites in general, right? So the complete bipartite is 2, right? And I think I already gave you an example of this, but for example, if I had K35, right? So it's going to have a lot of edges. Right? So still only need 2 colors, right? You color all these vertices 1, color all these vertices 2. Proper 2 coloring, right? Okay. So this brings us to kind of an interesting point, which is what's more general than bipartite graphs that we've had. Yeah, well, you can have any number of partitions, right? In general, though, showing that a graph has that many pieces can be split into a k-partite set. I mentioned before that that's actually NP hard. And the reason for that is that's equivalent to actually showing that the chromatic number would be K. Okay. So in general, the chromatic number, well, you can say that the chromatic number of Kn1, Kn2 up to Knl is equal to L, right? So this thing right here is a complete L-partite graph. Okay. Let me give you a small example here. So maybe let's do K222, right? So we're going to have 3 partitions. So this is a complete 3-partite set or a graph, right? And each partition has 2 vertices in it, right? So that's the 2, 2, 2. So I have 3 total partitions. This vertex is connected to these 4 vertices. And from that alone, I'll add in the other ones. But do you see that I am going, if I color this partition set 1, I can color this vertex also 1. Because within a partition, there's not going to be any adjacencies, right? So there's nothing wrong with coloring all the vertices within a partition the same. Same thing up here. Now I have to use a different color than this 1 because these are adjacent vertices, right? So I'll choose to use 2 for these ones. And then I come over here, and it looks like just from what I've drawn so far that I'll be able to do this with only 2 colors. But the thing is, I'm going to have the edges over here. And certainly, do we agree that there's a complete graph of size 3 in here, or you could say there's an odd graph in here. So I definitely need at least 3, but just from the structure of it, I know that I'm going to need a third color because pairwise, I have kind of these adjacencies, right? What you could think of the complete L-partite graph as is sort of a blown up version of a complete graph, actually. Let me explain that a little bit. Like maybe I'll draw one of size 5, and I think we'll call it a day because, okay, so set these up so they're in sort of a star pattern, right? Do you see that, well, you're going to add a lot of edges in. But what I'm kind of getting at here is if you add all these in, not going to be the prettiest picture, but you see if you zoom out that it looks like K5, right? Just haphazardly drawn, but that's actually a 5 partition, right? And it's K2, 2, 2, 2, 2, right? So thinking back to the fact that there's kind of a complete, there's definitely a complete graph within this. Do you see that? Complete, yeah. Oh, these ones, right? Okay, now do you agree that there's a complete graph of size 5 in here? So I need at least 5 colors, but it's kind of parallel with what's going on by coloring each of these. Each partition their own color. All right, so there's kind of a parallel argument there, but all right, we'll continue here next time. Well, actually, no, because next time we'll do a review. Okay, so we'll see this stuff again next Monday, right? So next time, let's just, what do you think was best? Did that help last time that we did the review? We'll just go over any maybe homework questions that came up, or yeah, and I'll make sure that the homework, the last one you turned in last week, right, will be graded before then. I think the other ones are all graded, right? We good? And you guys know that you can see comments that I wrote on them, right? Okay. Okay, so I'll see you next class. Bring questions. All right. And this stuff will not be on there. Maybe you'd like it to be on there. I don't know. Sometimes. Maybe it's easier than some of the other topics, but what was that?
So I find like that interesting, and like you can do that with like, it doesn't have to be a complete graph, but if you have like 3 partitions, then you like partition them like differently, kind of. I guess I'm not really saying it very well, but
if I give you a graph and then I ask you what's the minimum number of partitions that you need, so it satisfies the K-partite condition, that's
you can kind of
the same level of difficulty of showing the chromatic number, because if you give me the chromatic number, I can get those color classes, which is saying you have a K partition, right?
Yeah.
And if you have a K partition, then the chromatic number should be K.
considered NP complete.
Yeah, they're
And
both.
the ones that are like easy to verify are those.
Well, NP hard usually means that it is hard to solve, but you can verify it within polynomial time. So it still might not be easy to verify for us to do, but like a
Right.
computer could do it really easily.
Yeah.
What,
Yeah.
what happens they like proving this stuff? Like you said, like this is open. Like this is an open question. Like,
Yeah, the open question is whether or not NP is actually equal to P. So there's this strata of classifications in terms of how difficult some of these problems are.